case when the Q is a finite number. I mean, in general, Q could be infinite, but we do not consider those cases. Alright. So, that is a recall. The example that I have here, so over the property. So the property was I have this and I have Q XX is always non-negative. Q XY is always, sorry, this is non-positive, this is non-negative. Y equal X. And we already have QXX is always equal to the negative of the QXY. Alright. So to give an example, let's look at the Poisson process. I need to compute if j is less than, so if say y is less than x, then it's clear that I have a q, what is that, q of xy, which is the limit of what is that here? So nt, right? Where's the limit? So the limit of nt, forgot. Right. Yes.
Why the QXX can be negative? You say that the QXX is less or equal to 0?
Yes. So this is because in the finite state space, this, well, you think about like you have a PTXX minus the identity matrix evaluated, and this is 1 over t, alright? This is negative summation of PTXY, alright? PTXY over t.
Well, window is this part of the solution.
So, so this is PTXY minus 0 over t, but because the y is less than x, PTXY is 0 because this is probability. I have NTUY given basically like n naught being well being x here. Or somehow feel like that doesn't make any sense. This is, well, I guess we don't have this, right? So maybe let me do this. So t plus s, and then we have an s plus. This is identically 0. And so the limit is simply 0. No. No. Because suppose you already have x guests up to time s, then the number of the guests up to time t plus s cannot be less than x. So that's why this is 0. Yeah. So that is that. So now, suppose if I have x is the same as y, then I have q of x is again limit pt of x minus 1 divided by t. Now, what is this pt of x? So according to over that is simply, so we call pt x is basically e minus lambda t, right? Because this is the probability, and let's say n t in x additional n s is x. So no guessed up to time t, no more guessed up to time t. S is 0, t plus s. So this is x, yes. So 0 guessed. Approximately, that is supposed to be from the t to the 0 over 0 factorial. That is just e minus lambda t. And so, looking in over here, that will be limit of e minus lambda t minus 1 over t, and the answer will be negative lambda. So, that is the case x, y, so now, if, suppose now y is x plus 1, then what do I have? I have q x plus 1 is limit pt x plus 1 minus 0 over t, going to 0. So now this is e minus lambda t with 1 lambda t minus 0 over t. And the limit, now taking t to 0, the limit is simply lambda. Well, I guess that is because I already get rid of 1 t. So remember that is just e minus lambda t times lambda. So take t to 0, that is just lambda. Alright, so now if y is at least x plus 2, alright, now qxy limit pt xy minus 0 over t, t over 0. So here that will be given by what? So this is e minus lambda t y minus x over y minus x factorial t over 0 and sorry, divided by 1t. Divided by 1. So this is the same thing as I have the e minus lambda t lambda y minus x factorial times t y minus x minus 1. Okay. And the answer is 0. Because we already assume here y minus x minus 1 is at least 1. And so I do have one factor of t over here. If I take t to 0, that is just a constant multiplied by 0. So the answer will have to be 0. these are just algebra over here. All right, so the summary, the matrix, the rate of matrix Q for what's on process will be, so I have, okay, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Right, so this is always, well, so this is negative lambda. Have lambda here, 0, 0, 0. So you have negative lambda, then lambda, negative lambda, negative lambda. Basically, the rest is 0. Okay. As you can see, the sum on each row is 0. The sum of each row is 0, corresponding to that row over there. So the QXX, so the one in the main diagonal has to be non-positive. Every other has to be non-negative, and sum is 0. All right, this. Okay. So, what is the view around the Q here, right? Well, so the Q here can be thought as the rate, either stay at a location X or the rate leaving X to a location Y. And so part 2, construction of xt given Q, right? So now suppose I give you a matrix Q, how do you construct a Markov chain xt numerically? They come from the following theorem. So let me put the notation. So suppose I have x naught is middle x, all right? I modify tau to be what? Yeah. So the minimum, we'll say, or infimum is going to have the continuous time. Infimum of t, just that xt is not equal to x. Right? In other words, suppose I start the process from x. I will have to stay for some time, and the first time I jump out of it. So we plug at this. Right? So suppose I start my process at the location x. I'm going to stay for some time, up to a time tau is a jumping time. So I'm going to jump somewhere. Okay? The first time I leave okay, what is the theorem? The theorem says, the theorem says that a couple things. Number one, I have indeed tau is actually exponential with the parameter v and q and x. Right. A remarkable fact concerning continuous time is that the first time I'm going to leave x is actually exponential. Not really a coincidence here, not really. All right, not a coincidence. Okay, the rate is exactly the Q here. So you think about Q is like the rate keeping X at the same location. So then how does it jump? Number 2. All right. So the location of the jump probability X divided by the tau is equal to a Z. I guess I want to call it Y here. Is indeed QXY over the summation of the QXZ, where Z is not equal to X. And if you remember, that sum is just the absolute value of QXX. Okay. So in other words, once I wanted to jump, I'm going to pick a location Y. I want to jump to that location Y. Right here, sorry. So jump to here. I'm going to jump to Y with exactly that probability. And the third thing, which is also remarkable, is that indeed the X tau and tau are independent. Okay. So the location that I would jump to doesn't depend on the waiting time at the location. Well, so the theorems here are actually advanced. So we can, well, I'm not able to find an elementary proof, so let's just take it for granted. Okay, so let's just accept that for granted. And so now, given these theorems, you can see how I can construct my Markov chain numerically, given Q. So now, suppose it starts from location X here, time 0. I'm going to wait at some time, let's call T1, which is tau 1. Alright, and then I'm going to jump to, say, I'm going to jump to location Y. Alright, and so, so I want to have tau 1 is exponential of QXX, and probability I will jump to Y, so X tau 1, I guess it is equal to Y, and maybe let's call T1 capital T1. Y is occurring with probability QXY over QXX. Alright, then what I do next, I will just restart my process again. So starting from Y, I'm going to wait some time. Let's say this time here, which is my T2. And of course, the waiting time, tau 2, is another exponential. So, now, okay, well, I guess, okay, now tau 2 is exponential of Q, Y, Y. That's a good value, of course. Alright. So then independently, when I want to leave, I'm going to jump to a location Z, for example. Let's say I'm going to jump to a location Z. Jump in here. And the probability that I will go XT2 is Z is simply QYZ over QYY. Okay? And so on. Keep just start here from there. All right. Okay, so that is for the general picture. So let's think about the Poisson process. So that is the matrix for transition rate matrix for Poisson. Okay, so if you can see, it's actually very consistent as an example. So here, okay, I have Poisson process. Okay, so I start from time 0, 1, 2, 3. This is a T, this is C, right? So I'm going to start my Poisson at time 0 with no guest, the time 0 here, right? I'm going to wait for some time until the first arriving guest. That means at this time T1, I'm going to jump to 1. And remember, so tau here, first arrival time is exponential map, which matches the what? The Q at 0, 0, negative left. Alright. So then over here I'm gonna go to 1 with what probability? So the probability x of T1 V1 is Q01 divided by Q00 absolute value, which is lambda over absolute value of negative lambda, which is trivially 1. Right? So from 0, I can only jump up to 1 for sure. Obviously, when the first guest arrives, for sure, from 0 I can go to 1. And that's it. That is the only way out, right? And so similar, so you start from here, from 1 here, to get in the past, I'm going to wait until the second guest arriving at T2, and the rate here is still exponential lambda. Tau 2 is still exponential lambda. So that's indeed the Q of 1, 1. Remember, this is absolute value of Q11. Alright. Similarly, I'm going to jump from 1, I want to jump up to 2 with the probability 1. Alright. And then just start again from there. Okay. So I guess the example is clear on the construction. Okay. For the heuristic, okay, so here for the heuristic argument for this, we'll take a look at the lecture note. Okay, so why it should be exponential? Everything coming from the basically from the memory-less property of the Markov comes from Markov property. So let's move on. This is part 2. So I have the last piece concerning construction of the PT, the transition matrix given the rate Q construction PT given Q. Part 3. So there is a theorem on we have d pt over t is equal to ptq equal to q times pt. In other words, in terms of the entry, that means the derivative respective time, so d over dt of pt xy is, well, what is it? So pt multiplied by q, evaluated at the entry xy, two matrices multiplied together, evaluated at this location, is entry, the same thing as q times PT evaluated at N3 actually. Okay. And as a consequence, as a consequence, PT is actually given in terms of into the TQ, which is written as so what is that? The summation of T to the N, Q to the N over N factorial, and starting from 0, and in terms of, if I want to write explicitly, an entity matrix plus TQ plus T squared Q squared over 2 factorial plus L. Right. So PT, the transition matrix, can be written as a Taylor expansion of the involving the Q. Right. So remember, this is just the notation that they use. This is just a notation. All right. What really about the PT is written as this infinite sum of matrices. So if you already took a course in the OEE, then it should be familiar with you. If you have not, then let's just take it for granted. Okay? But however, this equation can be derived pretty quickly. Not really difficult for the differential equation. See this? Let me just mention the argument here. So I want to differentiate PT over T. So I have PT plus epsilon minus PT over T. Sorry, that's epsilon here. Limit as epsilon going to 0, entry wise. Okay. While the Chapman-Kolmogorov, this is the same as PT times P epsilon minus PT over epsilon, and so can be pulled out. For instance, I can pull out PT outside, PT outside multiplied with P epsilon minus the identity matrix divided by epsilon, and that is going to Q. So that's why equals PT times Q. Okay. And that is one direction. The other direction is, for instance, instead of writing this form, I could also go with P epsilon times PT minus PT over epsilon, which can be factorized out as P epsilon minus identity matrix times PT over epsilon, and that goes to Q in the limit of epsilon. So I have Q times PT. Okay. Not really difficult. Not really difficult. Well, I guess we call it Chapman-Kolmogorov, right? Chapman-Kolmogorov. Have PT plus S is the same as PT times PS, the same as PS times PT. Yeah. Okay. So Alright, so let's walk through the exercise to see. We do just formulate the transition rate matrix. First two problems are from the book. The third one is something else. Okay. But the ideas are similar to one another. Once you understand the formulation, then the rest is just pretty much computation. I haven't discussed like a stationary distribution, but we will do that in the following section. So for now, let's just formulate the Q. Let's just try to derive the Q, okay? Think about it. So like I have a barber shop, and so let's say this is the barber chair, right? Haircut here. This is the haircut chair, and then we have the two. How many weight? I have both chairs in the waiting room. In the waiting room, I have two chairs, all right? So this is the waiting room, okay? And so in order to model a Markov chain, so I have to denote by xt to be the number of guests in the shop at the time t. Apparently, how many guests I can have at a particular time t? How many guests I can have?
0, 1, 2, or 3.
Up to 3. So the state space is 0, 1, 2, 3. Alright. Obviously, you can only have at most 3 people at one time. So the next piece is the important piece to derive the Q. So to think about Q is the rate of jump from a location X to a location Y. Okay. So for instance, suppose I have let's consider 0 guests here. Let's consider 0 guests. Alright. So suppose there is no guest at the time t. Where can I jump to? I can only jump to 1. Because I cannot have a situation where like 2 guests arriving at the same time. I don't take that into consideration. You can only have 1 guest arriving. So Q can only jump from 0 to 1 with the rate. Well, that is the rate of the arrival according to the Boson process. with the rate 2. Okay. This is one arriving guest with the rate 2. Okay. And so apparently I cannot jump to 0, 2, 0, 3 is automatically 0. And as a consequence, from the fact that the sum has to be 0, Q 0, 0 is negative 2. Yeah? So you don't really have to think about this. All you have is to think about where I can jump to. Then the main diagonal will be just the negative of that sum, basically. Okay? Similarly, suppose at the time t I have one guest. That would be the guy being what? Is having haircut. Okay? So suppose one guest, that means the guy is having a haircut. And the 2 chairs are empty. Okay? So how do I jump from 1 to 0? How could I go from one guest to empty? Is that possible?
Rate 3.
That is because he finished the haircut, right? So what is the rate of having the haircut? So the rate of having the haircut is rate 3. So here from 1 to 0 is 3. Okay? You may be wondering, what if he already he already having the haircut up to time t, right? So say from 0 to t here, why do I still count from t? That's because the memory less property. The waiting time to have the haircut finished, starting from t, is the same as waiting time starting from 0. Memory less property. Okay. So that's why suppose he already waits up to time t, right? You may want to ask, okay, so when will he expect to finish the haircut? The answer is still the same thing. Still the mean is still 20 minutes, even though he already waits for t minutes. Okay. So that's why you have 3 over here. Similarly, how do I jump from 1 to 2? I can only jump from 1 guest to 2 guests is because someone is arriving. So someone is arriving over here. Fill in the waiting chair. So that the rate is still 2. Okay. And apparently I cannot jump from 1 to 3. I don't consider that case. So I have Q from 1 to 3 is 0. That's the consequence. Q11. The sum of everything taking the negative will be negative 5. Yeah? Okay. So I guess it should be clear now how do we get 2. But similarly for 2. Similarly for, suppose I have 2 guests at the time t. That means I have one having the haircut, one is waiting, and the other chair is empty. Great. So Q jumping from 2 to 3 is simply, what is it, right? Great. 2. Q from 2 to 1 is because the guy here is finished. What? Oh, that's the rate. 3. Okay. And Q, what else? Q2, 0 is impossible. So I have Q2, 2 is negative 5. Yeah. actually I have 3 guests in the system. So Q 3 to 2. It's only possible if one guy they having finished having haircut with the weight 3, and Q 3 1 is the same as Q 3 0, which is 0. That's impossible. So I have Q 3 3 is negative 3. Yeah. So to summarize, I have a 0, 1, 2, 3, 0, 1, 2, 3. What is that? Negative 2, 2. And then I have, is that negative 5? Negative 5. And I have, what is this? 3 and 2. So 3 and 2, 0. 3 and 2, 0, 0, 0, and what is the median rating? Yeah. And so, using the technically, using the Taylor's patient, remember, recall I have PT is a summation of G to the N, Q to the N over and factorial. So technically, we can compute the matrix PT technically given the rate. However, that is typically a hard problem. As you can see, it's a hard problem, and so we do not really care that much about the explicit formula of the PT. Okay. Is there any question about the derivation of the Q? Yeah, everything clear? Maybe the first problem could be a little bit confusing, but how about? Okay, so I have not discussed B and C, so let's do that on Monday. How about like the next problem, number 2? A computer lab. I have 3 printers. Okay. So think about like problem 2, for instance. Now let's think about problem number 2. Okay. I have 3 printers at one time. The printer will work and will break down within 20 days. Okay. So there are 2 repairmen working on the failure machine. Alright. So let xt be the number of working machine at time t. So now the model, the state space is still from 0, 1, 2, 3. I can only have at most 3 working machines at one time, and the minimum is 0. All are failing. Okay. So, as usual, so let's think about how can I have from. All right. So suppose I have 0 working machine at the time t. 0 at a time t. Now, how can I jump from 0 to 1? How is that possible? At what date?
1 over 2.
1 over
2.
1 over 2. Why is that?
because the expected value is the inverse of the rate.
Expected value they fix the machine is 2 days. So from 0 to 1 is because one machine is finished repaired. So this is a 1/2 because one machine is finished, is repaired, okay, is repaired with the mean being 2 days, and so the rate is 1 over the mean, which is 1/2. Alright? Yeah. And I cannot jump from from 0 to any other. I don't consider that case. Okay. Actually, that will happen with zero probability anyway, because that is there are continuous random variables, like a recurring time or a continuous random variable. So, for instance, you may argue like, okay, suppose starting from time 0 here, right? I have like say this is the repair one. This is repair number 2. Okay. So this is tile 1. Maybe call well, we get the one call say okay, let's call it say R1 is exponential with the rate 1/2. R2 is also exponential with the rate 1/2. Okay. So this is the recurring time, and they're both exponential and continuous. And so the chance you have 2 happening at the same time is 0. So probability R1 is equal to R2 is 0. Okay. So I cannot have 2 machines being repaired at the finished or repaired at the same time. I cannot have such situation because they continuous random variable. If they discrete, then that may be the case. However, this is continuous. So, you know what that is? No? That is because, well, how do you integrate this? You have, okay, you have R1 and R2, right? So the domain here is just a line on the plane. Okay, so suppose you want to integrate this. That means you integrate on this main diagonal over here. Like this is equal to integral, what is that? On this diagonal, right? Diagonal of the joint density. R2, R1, R2, okay? And so to think about like that, okay, so back in the 170E, let's say, suppose like you have an R1 running freely, and R2 is away, so this will be like R1 is from 0 to infinity for R1, but then R2 is just running from R1 to R1. R2. So if my bounds are the same, the integral is identically 0. Think about it like, so like suppose you just, so R1 is here, so the bounds for the R2 is just from R1 to itself. So if you have the same bound, then the integral is just 0. So that's why this is 0. It only works for continuous case, not for discrete. Anyway, so that's why you cannot have Q from 0 to 2. Okay, anyway, I already ran out of time. So let's continue.